Howdy folks, and welcome back to another week of physics. Today we're going to be covering chapter 6, which is momentum. Now momentum is a word that's used in a plethora of contexts. You can hardly watch a sports game without hearing an announcer talk about one team having momentum. You might have heard someone talk about a car or truck having lots of momentum, and then therefore being hard to stop. It's a word that you've probably heard in both a metaphor, but also possibly in a decent analogy, or maybe even its right context. But, as usual, we want to define this in terms of physics. So, how is momentum defined in physics? It is defined as mass times velocity. And we use the letter lowercase p to represent momentum. So p is equal to m times v. And as we've seen before, when you're defined by a quantity that is a vector, like velocity, you then are a vector as well. So momentum equals mass times velocity. Velocity is a vector, so momentum is a vector. That is, that direction matters. And what direction is your momentum? It's in the same direction as your velocity. So if you're moving to the right, you have a velocity that points to the right. Your momentum would also point to the right. Well, what about the units of momentum? As soon as we have an equation, we can think about what the units should be. P equals mv, so the units of P are the units of m times the units of v. That is kilograms for mass, meters per second for velocity. The units of momentum are kilogram meter per second. And you might be waiting for me to tell you what that's equal to, but there isn't anything. There's no special unit for momentum. Its units simply are kilogram meter per second. Now, the other quantity that we're going to study, apart from momentum, is impulse. And impulse is really closely related to momentum. A change in momentum is called an impulse. It's sort of the kick or push that causes something's momentum to change. And so if we define impulse, it is given by the letter capital I, and capital I is simply just defined as delta P, or the change in P, the change in momentum, which is your final momentum minus your initial momentum. And as such, the units of impulse are identical to the units of momentum. They just simply are kilogram meter per second. It's how much your momentum changed. And you measure that in these same units as momentum. But impulse also has another definition. So we've said that a change in momentum is an impulse. Well, let's ask the question then, how do you change something's momentum? Well, it's defined by mass times velocity, so you either have to change its mass or change its velocity. Now, while it is possible to change something's mass, it's not a very common situation. Essentially, we might work a problem or two with this sort of example, but if, say, something's like leaking water as it moves along, or you're piling dirt onto something as it's moving, or you drop a plate, like a weight onto a skateboard as it rolls by. Well, its mass can change in those situations, but those aren't really very naturally occurring. The one situation that this matters a lot in is sort of rockets. Whenever you're blasting off in a rocket, you're burning up your jet fuel, and so your mass is changing. But that's a little more complex than we're going to deal with in Physics 1030. So if changing something's mass isn't really the normal way to change its momentum, that leaves velocity. Changing something's velocity is usually what's going to happen whenever you're changing its momentum. And we know from chapter 2 that a change in velocity is defined as an acceleration. And from chapter 3, we know that an acceleration requires a net force. Thus, to change something's momentum, you need to apply a force. And you don't apply that force forever and ever and ever. You apply it for some finite amount of time. some kick. Whenever you kick a ball, or swing and hit a ball with a bat, or simply tap on your accelerator in your car, you only do it for a certain amount of time. And that is how we define impulse in a second way. Impulse can also be defined as force applied for some amount of time. I equals Ft. Well, what would the units look like under this definition? Well, the units of impulse would be the units of force times the units of time. That is, they would be Newton times seconds, or Newton seconds. And that's different than kilogram meter per second. At least it looks different. If we take a closer look, though, upon further inspection, newtons times seconds, well, a newton is a kilogram meter per second squared. So a kilogram meter per second squared times seconds, we cancel 1 unit of seconds on the bottom here, and sure enough, we're left with kilogram meter per second. Newton seconds are identical units to kilogram meter per second. They just look a little bit different. They're represented slightly differently, but they mean the exact same thing. So, if you know much about momentum, you might have heard that momentum is conserved, and it is. Just like energy, momentum is a conserved quantity. But we're talking about the entire system. So just like with energy, energy can be traded from one thing to another. It's the total amount that is conserved. And the same goes for momentum. We're not concerned with any individual object's momentum. Surely your momentum can change. But if we do some accounting, the total momentum at the beginning needs to equal the total momentum at the end. In equation form, this means the sum of all the initial momentums equals the sum of all the final momentums. Remember this capital sigma, we've seen this before. Capital sigma, capital Greek letter S, means summation. It means add them all up. And so really this is saying, okay, well, object 1's initial momentum plus object 2's initial momentum plus object 3 and 4 or 5, however many things you're concerned with. You add up all their individual momentums at the beginning, and they better equal all of their momentums at the end. That is, we then look at object 1's final momentum, object 2's final momentum, and so on and so forth. Now, in this class, we'll keep things relatively simple. We'll probably stick with 2 objects at a time, but it can go as large as possible. You can deal with millions of objects at a single moment, and in fact, large simulations of things like galaxies might try to keep track of this, keep track of the momentum of every individual star. But that's way beyond our pay grade. In this class, we'll probably stick to 2 objects at a time. And the important thing to realize when looking at this equation is that those individual momentums can change as long as the total momentum remains the same. If the total momentum remains the same, you have conservation of momentum. That means that, object 1 can bump into object 2. And then maybe object 1 isn't moving anymore, but object 2 is. Object 1 has sort of transferred its momentum into object 2. The individual momentums can change, but when you add them all together, everything at the beginning better equal everything at the end. And we'll look at a couple of examples of this before the day is over. This is very commonly used to solve collision problems. And we will look at 2 types of collisions: elastic collisions and inelastic collisions. In an elastic collision, that just means the objects bounce off of each other. An inelastic collision means they collide and they stick together. And there's something special about that we'll look at here in a moment. There's also some special rules about them bouncing that I'll explain momentarily as well. But that is the basic introduction to momentum and impulse. We'll come back in just a moment with some examples of elastic and inelastic collisions, as well as elastic and inelastic impulses. See you guys soon.